Welcome to this early career researcher interview for Thomas Homan, who's one of our lucky finalists. Thomas went through the competition, tight competition this year. So Thomas, from the University of Bath, do you want to get your poster up and talk us through your poster?
Yeah, so this is basically an overview of my PhD project. The focus is on high resolution modelling of pollutants in a Dorset Chalk stream. So I'm looking at the River Froome in Dorset. Just a bit of context then. So firstly, what are the pollutants I'm interested in looking at, which is what we call emerging contaminants, so things like pharmaceuticals, illicit drugs, industrial chemicals, pesticides, etc. So these contaminants they're called emerging contaminants because although their presence is known and their potential to cause adverse effects are also known, not the knowledge isn't yet comprehensive, and there isn't a regular sort of monitoring or any sort of regulation in place yet for these chemicals. So what impact are they having? I mean, as I've mentioned, they can have adverse effects both on ecosystem and human health, things like endocrine disruption, reproductive toxicity, and for us as well, things like antibiotics are obviously and antibiotic resistance is a health risk. So they mainly find their way into rivers through constant discharge from sewage treatment works, which leads to a bit of a pseudo persistence. Not much yet is known really on the fate and transport of these compounds in the environment, and really what that leads to is when you're trying to risk assess these contaminants, the concentration that organisms are exposed to is a bit of a rough and ready estimation at the moment. So if you look at European Medicines Agency, they typically apply sort of steady state risk assessment models that just assume a sort of a dilution factor. So what I'm interested in is developing a high resolution model that can actually predict both the temporal and spatial variation of these compounds in the environment. So if you look at this graph here, a risk assessment model at the moment might predict a kind of an average flatline concentration, although there will probably be confidence intervals. But in reality, the concentration is probably highly variable. And what I'm interested in is what sort of, what's the significance of this variability for as an ecological risk, and so what implications are there for both sampling and risk assessment. So when you get on to look at the aims and objectives, it might become a little bit confusing because I'm actually first developing a model for nitrogen and phosphorus species. So your standard nutrients that you see in our rivers, and then I'm going to use the inferences from that modelling process to then adapt the model for emerging contaminants. I can see why that might cause a bit of confusion, but it's limited by the fact that it's technologically and financially unfeasible to monitor these emerging contaminants at high resolution. So the data really is only there for these nitrogen and phosphorus species. But if you look, for example, at just the loading side of things, so by monitoring nitrogen and phosphorus species, you'll be able to understand sort of diurnal variation at sewage works, and potentially sort of impacts from rainfall and other environmental parameters. And then you could even link that that variation or predict that variation at sewage works stochastically based on sort of the demographic of the catchment area and domestic habits. Now, if you link that then with a much more high resolution spatial prediction of your per capita consumption of, not your per capita, but your catchment consumption of pharmaceuticals, for example. So if you take sort of postcode prescription data, you can then really refine your prediction of the loading into the river. And then obviously things like your hydrology, if you can accurately simulate your hydrological processes in relation to rainfall or hydrogeological characteristics of the catchment, then obviously that's going to be the same for both whatever contaminant you're looking at. So anyway, that I'll be using those inferences to help sort of then estimate what the kind of variation would be of a emerging contaminant. And some of the parameters will be better proxy for that than others. Obviously, their fate will vary, will be quite different to the fate of an emerging contaminant like a pharmaceutical. And then that will be something that I'll have to just make assumptions and predict. And I think at some point you would need to at least validate that with a good amount of data to make sure that your model is a good prediction. So in terms of the model development process, I'm using software from DHI. It's the Mike software modeling suite. And that was really chosen, I compared against other softwares that are available and had a list of criteria to select based on, and this seemed the most suitable to my needs. So at the moment, I've developed the hydrological model for the river. A dry hydrological model hasn't yet included rainfall or base flow processes. And I've been validating or collecting data to calibrate that model. So we've deployed these pressure transducers, banners and divers in the river, which give you a continuous estimate of river stage. And we've been putting those in strategic locations. So sort of upstream of structures to understand flow splits between different stream channels. And that's helped to calibrate the hydrological model. And I've also been doing flow accretion analysis of the flume to understand where the key inputs are from spring sources, which will also be used to characterize the volume balance for the hydrological model. So now really I'm focusing on modeling the water quality, and at the same time I'm currently in the middle of a monitoring campaign. I just started actually yesterday. So what we've got at the moment is about 6 different water quality SONS sensors. Some of them, or most of them, can monitor nitrate, but the other 2, so 4 can monitor nitrate, and 2 just sort of standard sort of turbidity, conductivity, temperature, dissolved oxygen, etc. So they've been placed at strategic locations, which includes the sewage treatment effluent, and also sort of main tributary inputs. And I'll be using that data then to, as I say, calibrate and validate the water quality module. So as I say, they're currently deployed at the moment. They'll be there for the next month. We decided to focus on this period, low flow period for the river, where it's going to be most ecologically sensitive to sewage pollution. And yes, as I say, got 6 sensors, and to try and get as much sort of spatial information as possible, we're going to be moving them every 2 weeks. So we've got first half of the period monitoring the upstream of the river, and then the second half is going to be the downstream river. And that was really a financial constraint more than anything, but it was the best use of the sensors that we had. Okay, so what I want to achieve once I've actually set up this model, well, I've got sort of a number of research questions, but as I say, linking it back to the start of my little talk here, where I've said about what are the implications for this high resolution variability. So I think first it would be to confirm, whether this is actually occurring. So what kind of variation do we see? Is that variation caused by the loading, so the sewage effluent loading variation? So is that signal expressed downstream, or is it more a consequence of the sort of the in-stream fate processes, that variability or hydrology? So I think the question would be to look at, say, what are the sensitivities to those different factors, and what are the main controlling factors on variability, and then looking at how that changes maybe seasonally, but also on a sort of intradaily perspective. And then in terms of linking it to predicting the risk of emerging contaminants as well. So what are these spikes or these troughs in concentration? What impact is that having ecologically? And I won't in my PhD be able to go into the effects too much, but I'll be able to sort of make a rough and ready estimation based on comparing it to predicted no effect concentrations. Then in terms of the impact, you could look at, so if it's a high resolution model, I know CSO and storm discharges are a topical conversation at the moment. You can look at potentially the impact of those transient pollution events on the ecology, and whether there is a concern for even sort of acute toxicity to occur. And then really, once a monitoring campaign for these contaminants would be highly expensive, but if you have a model, it's a cost-effective way of predicting the risk, and will help you screen maybe the most important pollutants in that catchment, which you can then use a more targeted monitoring campaign to determine really what the concentrations are and what impact it's having. It helps you to narrow your focus. And also it helps any stakeholders involved to assess their risks, assess what their impact they're having is on the catchment. And then ultimately that will lead to better mitigation and abatement strategies. And then you can obviously as well use the model to simulate the effect of those abatement strategies. So really that's the kind of the strategic goal that I'm aiming towards. And obviously I'm focused on one catchment here, but really to make this PhD have the greatest impact, I think my last chapter of my thesis, I'd like to focus on how I could build all this information into a standardized framework, if you like, that anyone could apply to any catchment to help better understand the risk in their catchment. Really that would be the kind of the high end goal of this project, really.
Fantastic. Thank you, Thomas, for a comprehensive summary of your PhD project and your poster. Certainly looking forward to welcoming you to WEM, where you're going to be presenting to us in live, and look forward to seeing you in October.
Yeah, look forward.
Thanks, Thomas.